Hi learner, I welcome you on board this session. The topic of this session is pressure altitude and it is entitled to the subject flight mechanics. The target audience for this session are GATE aerospace aspirants, aeronautical and aerospace engineering students. We have traveled so far in the syllabus and we have covered the category basics under the core topics and we have seen the following concepts under the category basics. Now we will be focusing on airplane performance and we will proceed to the concept pressure altitude. In the previous lesson, we did learn about basics, and the link to the previous lessons will be provided as a playlist in the right top corner. So it will be provided over here. In this session, we will be knowing about the types of altitudes, specifically pressure, density, and temperature altitudes, and we will be knowing the practical significance of it and the basic general method which is used to determine these altitudes and the unit conversions. We will also be seeing an alternative method to measure these altitudes. In the previous lesson, we did see the geometric absolute and geopotential altitude. So, under the types of altitude, we will be further proceeding to know about pressure, density, and temperature altitude. Here is an international standard atmosphere chart. So, if we particularly know the value of pressure, density, temperature, either one of it at some particular point, we can calculate the altitude, and these altitudes are known as pressure altitude, density altitude, and temperature altitude. Before getting into it, we need to know what is pressure. As we know, pressure is a force applied on any object. Let's get into details of it. It's generally a force, but specifically when we see the direction of it or the nature of it, pressure is a perpendicular force. That is, it is applied in the perpendicular direction to the surface of an object. When we refer to pressure, there are several kinds of pressure, such as hydraulic pressure, fluid pressure, or similar kind of pressure. But here in this session, we will be referring pressure as atmospheric pressure, and it is normally measured in inches of mercury, that is Hg, or millibars, or sometimes in pascals. When we refer to atmospheric pressure, the major constituent of atmosphere is air. So even though air is light in weight or lighter, it does have some mass. So according to the laws of physics, if some particular body is having mass and it is present within the Earth's atmosphere, it is affected by gravity. So it is basically attracted by gravity. So it must have some weight. Weight is nothing but the amount of gravitational attraction. So if it does have weight, it also has a force. Since air is a fluid substance, fluid consists of air and liquids. Generally, there is a misconception that fluids only consist of liquids. No, it isn't. So, as air is a fluid substance, this force is exerted equally in all directions. So, if any body is present in that liquid or air is mentioned over this session, it is going to be affected by the pressure, by the force. This force is known as pressure. The pressure of the atmosphere, it isn't static, it is dynamic, and so it varies with time and location. Thus, we need a standard model which we can refer, or a static model which can be used to calculate the values at some particular point. So, by the International Civil Aviation Organization ICAO, a standard model is proposed or suggested for being followed in order to calculate the values at some particular point. So this is the International Standard Atmosphere Model, and we discussed the basic derivations of International Standard Atmosphere Model, its existence, and how to derive the International Standard Atmosphere Model in the previous session. So this standard atmosphere model is being used to calculate the pressure, density, and temperature altitude. Now let's define these altitudes: pressure altitude, density altitude, and temperature altitude. As I mentioned before, if you know the pressure at some particular point, you can measure the altitude of it, and this altitude is known as pressure altitude. Similarly, you can also define the altitude based on the density and temperature. Here, a major point is to be noted that the pressure at mean sea level isn't zero. Basically, we are being exerted by some force, that is, we are being experiencing some pressure on the surface of Earth or the mean sea level, which is also known as the standard datum plane. So the pressure which we are feeling around right now is sta- statically modeled to be 29.92 inches of mercury. So here Hg is the mercury, and it can also be termed as 1013.2 millibar. Pressure is generally measured by the instrument barometer. Now, getting to know about density altitude, as I said, if we know the density at some particular point, we can derive the altitude of it. We can also achieve the density altitude by correcting the value of pressure altitude for non-standard temperature. Non-standard temperature is nothing but the temperature with which differs from the standard atmosphere model is known as non-standard temperature. So if we correct for those variations, we can achieve the density altitude. We need to note that a decrease in air density means higher density altitude, and an increase in air density means lower density altitude, which means that if the density is high, the altitude is low. So if the density is low, the altitude is high. Temperature altitude. If we know the temperature at some particular point, we can measure the altitude from it. So basically, the altitude measured by knowing the temperature is known as temperature altitude. What is the practical significance of these kinds of altitude? Let us consider a real case example. Imagine that you are in an airplane flying at some real geometric altitude. Geometric altitude is nothing but the height from the surface of the earth or mean sea level to the point of reference. So let us consider that we are flying at some particular geometric altitude, which is notified or denoted as Hg. So you are just measuring the actual outside air pressure to be 20.6 inches of mercury. So you are measuring the pressure and temperature at this point at some particular geometric altitude. The pressure is 20.6 inches of mercury, and the temperature is around 260.5 Kelvin. So you know the pressure and temperature. So as said, we can determine the altitude at which we are flying, as we know two parameters. When we use the standard or international standard atmosphere chart, so this is international standard atmosphere chart, and it would be generally provided in exams as an attachment or appendix. So when we are referring it, we know that we have calculated or measured the pressure at this altitude. So if I see the pressure range, and if I refer the altitude range of it at that point, we can find out the altitude at which we are flying. Similar procedure can be used to determine the temperature altitude. So let's find the pressure altitude. As we know, the value of pressure at the point we are referring is 20.6 inches of mercury. So we also know that the pressure decreases with increase in altitude. So here the altitude is increasing from 0 to particular amount of feet. So we need to locate the 20.6 inches of mercury. When we follow the international standard atmosphere chart, it is in this range, or it is particularly over here. So here it is. So if we refer The altitude range, which is parallel to this pressure, we can determine the altitude at which we are flying. So when we refer the altitude range, which is in parallel with 20.6 inches of mercury or the pressure, we can see that we are flying at 10,000 feet. Okay, it is determined. At the same point, we are also measuring the temperature. So the temperature is 260.5 Kelvin. So we need to find the particular temperature in this particular scale. So 260.5 ranges over here. So if we refer the parallel altitude range, we can see that we are flying at 14,000 feet. So based on the pressure altitude, the altitude is 10,000 feet, and based on temperature altitude, the altitude is 14,000 feet. That is, we are actually obtaining two different altitudes. We can't be flying at two different altitudes simultaneously. But based on this model, it is the inaccuracy we are achieving, that if we refer the pressure altitude, we are getting some point of altitude, and if we are referring the temperature altitude, we will be obtaining some other kind of altitude, and the geometric altitude may be totally different. This is generally obtained because the pressure, temperature, and density are in constant and they are varying. So at some particular point of time, it can be a rainy day or a sunny day. So the temperature and pressure will be differing based on the climate. This is necessary for international standard atmosphere chart and necessary for standardization so that a static model can be used. So we do have the pressure. How to measure the pressure altitude if we are not provided with the international standard atmosphere chart? Generally, in gate examination, it is difficult that they provide the standard atmosphere chart. They may provide though in most of the cases. So if in rare cases, or they are thinking of evaluating our basic capabilities, we need to know how to achieve the pressure altitude without using the standard atmosphere chart. And we will also verify the answer with the standard atmosphere chart model. So here is the formula for obtaining the pressure altitude without using the international standard atmosphere chart. So pressure altitude is equal to the difference of standard pressure, which is at the mean sea level, to your current pressure setting, or the pressure which we have obtained or read using some instrument, times 1000. So basically here it is mentioning in inches of mercury, and it is typically assumed that uh, with every 1000 feet there is a drop of 1 inch of mercury. So that's why we have multiplied it by 1000. So for every 1000 feet increase or decrease, there will be variation of 1 inch of mercury in the instrument. Here we have neglected the field elevation. So this is the basic elevation, that is above mean sea level or below mean sea level altitude of the field. If we are considering some airport or some other kind of place, so it isn't on the mean sea level, as the mean sea level model is the standard model which has neutralized this. So considering this as earth, so if we are in some mountain and this is the sea level, so the altitude is going to differ, and the basic height of which, or the basic height of the land isn't in accordance with the mean sea level, so it is elevated. This elevation is termed under field elevation, the height difference from the mean sea level. Okay, now we are referring the mean sea level condition, so we can take the field elevation as 0. We also need to know that if there is higher pressure, it means that we are in lower altitude, and if there is lower pressure, it means that we are at higher altitude. Now let us assume an example for understanding purpose. Let's say we measure 24.92 inches of mercury at some geometric altitude. So what is the pressure altitude? So, as the formula suggests, so it is the difference between the standard pressure and the measured pressure. So, standard pressure is 29.92 inches of mercury, and the pressure we have measured is 24.92 inches of mercury times 1000. So, we are obtaining approximately 5000 feet. And we also need to know that GATE Aerospace Engineering doesn't ask direct questions. Or even though this is so simple, the question may be twisted such that we have arrived at the answer, still they will be asking the answer in meters. So, how to convert the answer we obtained, that is in feet, 5000 feet, to meters? So, here feet to meter conversion needs to be known by the student in order to answer this question. So, if we are obtaining 5000 feet, and if we multiply it by 0.3048 times, we will be obtaining the meter convention or SI unit of the answer, that is 1524 meters. Now let's cross check this with the standard atmosphere model's answer. So here our pressure was 24.9 inches of mercury. So here we have the 24.9 inches of mercury. So if we cross check it with the parallel altitude range, it is 5000 feet or 1524 meters. It is also 1.524 kilometers. So the unit conversion needs to be known. And here I would like to also mention the difference between the pronunciation or spelling. We generally write METRE. So METRE in British English is used for measuring the distance, and METER is generally used to specify some instrument such as altitude meter, barometer, or similar kind of it. Now let's know an alternative method to calculate the pressure altitude. We already knew about the pressure ratio and density ratio for isothermal and gradient layer. If we are able to measure the other values, we can determine the altitude. And the altitude which we determine will be the pressure altitude or density altitude as it is. So by rearranging the equations, we can find the altitude if we know the pressure and density ratios. In the previous lesson, we will be finding out the pressure ratio. So here we will be determining already knowing the pressure ratio, and we will be trying to determine the altitude. So for gradient layer, we know that temperature at some particular point at which we are observing is the summation of the base temperature of that region plus lapse rate times the height difference. So if we know the temperature at which we are measuring, or the altitude we are measuring, and the base temperature, the lapse rate, and the base height, that is 0 in case of gradient layer, uh, we can determine the value of h by rearranging the equation. And temperature can at that particular altitude can be obtained by rearranging these equation. So we are talking about the gradient layer. So if we rearrange this equation to find out the t value of t, we can obtain similar kind of equation. So when we substitute this value in equation 1, we can obtain that. So here is the equation 1. So if we substitute the value of t over here, we will be writing it as t, uh, t1 by a, that is lapse rate, which is the division term which is taken to the LHS, and it is also transferred to the LHS. So it is transferred to the division term. So T1 by A times P by P1. P1 is nothing but the pressure at the base of the altitude which we are referring, to the power of minus lapse rate times the gas constant divided by the constant acceleration due to gravity. So here we are seeing that T1 by A term is constant, and if we take this as constant or common, we can get a common term, and the specific term is inside the bracket. So this is how we can determine the altitude, that is pressure altitude, by using the known derivation of International Standard Atmosphere Model. So this is an alternative technique, and in a similar manner, we can also measure the density, altitude, and there are two different equations for this region, and we need to specifically rearrange the equations based on the layer which we are measuring. That is, it should be either gradient layer or isothermal layer. Topography does play a major role in this learning for GATE Aerospace Engineering. And for getting a deeper perspective, you can read the Pilot's Handbook of Aeronautical Knowledge, the 2016 version. The chapter 4 of it, that is page number 90 to 93 of this version, does have some practical knowledge, and you can obtain basic understanding by reading this. This book is freely available with NASA's website. You can download it from online for free. And for getting a detailed perspective of this concept, so you can read the Introduction to Flight by J.D. Anderson, the seventh edition of it, and the page numbers in which this topic is ranging is 125 to 133 of this particular edition, seventh edition. That's it for this session. We have learned about the types of altitude, specifically the pressure, density, and temperature altitude, and we also learned to know the method to determine the pressure altitude. Thank you. Let's crack GATE Aerospace Engineering.